right, good morning, everybody. My name is Ingo Lütgebulle from Bosch Corporate Research, and I will be talking about something which is probably not so familiar in this community. And it's a bit more than just debugging your robot. It's more like designing it so that you don't have to debug so much. But first, maybe what's this determinism in robotics software? What's this about? This is probably not so familiar. So one thing is what we often hear when we look at robotics is that it worked for the video, so it works now. And well, let's just say that if you really want to go into productive systems, sell systems, make your customers happy, that's not going to cut it. The system should behave the same way every time you use it. And that's what we understand as a simplified version of determinism. So for this talk, I would like first to give you all a little bit more of an introduction to what kind of problems we can encounter when the system is not deterministic. And I will also say what I exactly mean by determinism, because the scientific definition of that is maybe a little bit too strong. So to do that, after that, I will explain a little bit about how ROS does things internally, so to put the determinism stuff into perspective and also give you some information for designing your systems. We'll outline some common practices, how people handle these issues, and also outline a couple of packages that can help you. And then I will shortly look at measurements. Actually, I will show measurements throughout, and then at the end I show you how to get those. So this is just the outline. So first some definition, motivation, background, and then the info. Right. So by the book definition of a deterministic system is some system that will always produce the same output when starting conditions and inputs are the same. So for robotics, that's often problematic because we have randomized algorithms and machine learning things which depend a little bit on their internal, on something else than just their state. So what we are mostly interested in is if you take a step back from the algorithms and look at deterministic execution, so the goal is that our algorithms are called in the right order. Then what they do internally might or might not be deterministic, but as long as they're called in the right order, that's already a big step. And the other part, which is one thing which is quite problematic for ROS, is deterministic communication. Because as you all know, ROS uses TCP communication by default. That means everything goes through the kernel once. This is a best effort type communication. You have very little guarantees on that. And again, here we use a slightly simplified goal. We just say, if we have a communication link between A and B, the communication should be always either occur before B executes or after B executes. And this is how exactly what that means maybe will become clear later. Right. So why are we actually interested in that? Why should we care, right? I mean, actually when I gave this talk in the ROS industrial context a couple of times, and sometimes people come up to me and say, hey, our systems work. Why should we care? And I said to them, are you really sure that your system works all the time? And if you say in many cases this might not be so important, but this example here is like this robot is moving to the left, and you see there's a person coming there, and we had better be sure that the robot can stop in time. Particularly, in this situation it's unloaded, but this robot can carry 250 kilos of payload, and plus some weight for the robot. You really wouldn't want to hit a human with that. So in essence, what you want to ensure is that this situation, the robot has this red light on, it means it's stopped, and so the person can pass, and then the robot will do that. So how do we usually do that? We say, okay, how can I be certain of that? I have obstacle avoidance. It's been in robots for ages. Every mobile robot has obstacle avoidance. But how does it work? So what do we need? First of all, we need sensors. sensors to, actually detect the obstacle. And then the question is, how often do I get data from my sensors? And what's the delay of the sensor? So I need to know that. Then I have an environment model, because I can't see everything. Few sensors, few prior information, like where was the robot when my sensor data was taken. I then have to replan, brake, drive around it, whatever. And, of course, I need to be sure that my actuation system actually does what I wanted to do. And I need to combine this in a trustworthy manner. So for the purposes of this talk, my focus will be on the last item here. Because all the other stuff, that's fairly well known. We have methods for that, we understand them fairly well. But, actually combining them all in a working system, that's still a challenge. And just want to give you this image here, while I pour myself something to drink. So what is this? This is a look at the ROS navigation stack and the move base in particular. And what I did was, I looked at, I get a laser scan from my laser scanner, it gets into the move base, and then the move base needs to output a reaction to that, like maybe drive around an obstacle. And I took a measurement of how long that takes. And as you can see, I hope you can see that, I marked it, like this takes some time, right? So the processing time in the move base. And here on this image, we see on the x-axis is the elapsed time of the experiment, and the y-axis is the time it takes for the move base to react to the laser scan. And what we can see is that this varies a lot. So in the best instance, we have a reaction to the laser scan at 11 milliseconds after the move base received it. And in the worst case, we have 235 milliseconds after the move base received it. And what we can also see is that there seem to be these stable periods where we have a certain reaction time, but it jumps. And so the first thing that people are familiar with the move base might be wondering is, the move base runs a 10 Hertz control loop. So there should be at most 100 milliseconds reaction time, right? If you assume that. But, and so this is true here in this example. The move base in this example, it outputs a command every 100 milliseconds, plus or minus a couple milliseconds for planning, delay, and jitter. But the thing is, this planning command is not always based on the latest sensor data. Sometimes the cost map integrates the latest sensor data after the command is already output, and that's why we get these reaction times. And so that's sort of the running example that I will use throughout the talk to give you an idea of what this is all about. Okay, so what are the causes for that? First is sensor data processing. We often see bad timestamps in sensor data, and we also often see that people don't use real-time processes to receive sensor data, even when the data arrives at a fairly high rate. This can lead to lost data. And everybody who uses a Kinect or a FreeNect with a FreeNect drivers will have seen messages like, I lost the data. And then we have sampling effects. I will explain that a little bit later, also in more detail. But what this means is that we have different threads running asynchronously to one another, and they communicate. And one needs an input from the prior one, but it actually runs before it receives the input. And so sometimes it runs before it receives the input, and sometimes it runs after it receives the input. So this is sort of like sampling continuous signal in non-equidistant intervals. So, and this is what we call the sampling effect. Great. So just to also give some perspective, this is not applicable to all robotic systems. This is most important for things where the output depends on the input, which is almost always true. And it's also for dynamic environments, when the environment actually changes fairly quickly. And also when you can't predict very well. And I also assume a typical ROS system, which is running on Linux, has multiple nodes, and you have typical bus systems. And I will, in my talk, everything I say is focused on the critical loop. like mostly the reaction loop. Not everything in your system really has to take care of this, of these aspects. I mean, it's good if it does, but it's also quite a bit of effort. So let's just say you should do these kinds of, you should apply this knowledge mostly to the critical loop, at least. Right, so a little bit of background on ROS. You probably have seen something like this. It's not on the wiki, but it's fairly well known. So there are multiple threads within a ROS CPP node. We have a network thread, which asynchronously reads and writes to the network. There's a timer thread, we know which manages all the timers. And both of these threads, they put callback pointers into the callback queue. And then there's a spin thread on the side, which always takes the newest item from the callback queue and executes it. And then on the bottom there, the TF has its own thread. This is so that you can wait for transform without blocking. I mean, you can disable that actually, but it's on by default. So that's the number of threads that you have in your CPP. And then in the callback queue, to give a little bit more information about that, so the callback queue is a sequential queue, has no priorities or anything. I mean, there's people working on that, but by default it doesn't. And so it has a reference to a certain message and a subscription queue. And the subscription queue is allocated per topic and per callback to that topic. So if you have like 2 callbacks to the scan topic, then you will have 2 subscription queues. And this is also, it's quite interesting in that if you have multiple messages waiting to be processed in your callback queue, they will refer to the same subscription queue object. But in the subscription queue object, there's another queue where the messages are inserted in order. And then whenever the subscription queue object comes to the top of the callback queue and gets processed by the spin thread, the topmost item will be taken from it and being processed. And then it's done. And then the next reference a bit further down in the callback queue will process the other items. Right. And the size of the subscription queue is defined by the subscribe call, the queue size argument, and yeah, the other thing I said. And one thing you should notice is that the subscription queue can be limited, right? And if you have an item sitting in the callback queue waiting to be processed, and the subscription queue is full, and you have another message coming in, it will replace the oldest, or not replace, but it will kick out the oldest object in the queue and put the new item at the end. But it won't add a new entry into the callback queue. It will keep the existing entry in the callback queue. Only when there's a new item added, then it will add a new item. So this can lead to newer messages being earlier in the callback queue. Just something to keep in mind. Right. And something you should also know, if you have 2 callbacks assigned to the same topic or more than 1 callback in general, then they will be processed in order of their subscription. Okay, so the next thing up is, most of ROS systems run on Linux. And so as we saw, ROS CPP internally has a number of threads already. We also have, if we have multiple nodes, we have even more threads. So all of these threads are scheduled by the Linux scheduler. And the Linux scheduler, as you might know, has a hierarchy of scheduling approaches. The highest one is the real-time scheduler, which is a priority-based rank queue. But that's only used if you take explicit measures. The one that's used by default is the fair scheduler. And the fair scheduler doesn't have any notion of importance. It doesn't know that your motor controller drive control loop is more important, for example, than your symbolic planner or something like that. What it does, it tries to allocate fair amounts of processing time to all the processes. Yeah, so I think I'm getting a little bit behind time here. I'm trying to speed up. Anyway, what I'm just saying is that you should be aware that the fair scheduler doesn't have any notion of priority. And that's what if you really need fixed priority processing, you need to use a real-time scheduler. And the real-time scheduler, again, in the Linux kernel is not really real-time. I will give you an example. So first of all, this is wake-up latency. And do you actually see my mouse here? Maybe not, huh? Yeah, the pointer. Let me try that. Anyway, whoops. Let's see here. So here on the left-hand side, those are scheduled. That's the reaction time. So I have a loop every 200 microseconds. I try to activate it, and that's the wake-up time that it takes from the point it's activated until it actually runs. So for real-time processes under load, this is all while running a stress test. This is below 10 microseconds on the average, and for a non-real-time process, it's between 50 and 60 microseconds on a Core i7, so fairly powerful machine. But what we also see, we have significant outliers. So we do have here, down here, this is microseconds, so here 2 milliseconds for 6 milliseconds. So we see there are these outliers here in the histogram. So what I'm trying to say with that is that you can't expect that your process runs as soon as it's ready. There will be delays, and the delays can be significant. They can, and we can, this is a 10-second example. If you run for a couple of minutes or hours, we see bigger delays, particularly if the system is stressed. And that's why you want to use Linux with RT preempt. So the reason for that is the kernel subsystem, it can block real-time processes in the vanilla kernel. So if you want to do, like what we did, some testing on that. So if you have UDP traffic, for example, you can easily get these 5 millisecond delays. If people access procfs in a stress testing environment, which is probably rare, but could happen, then we even for real-time processes, we see up to 60 milliseconds delay. So use the real-time preempt patch. That's where you can get it. We're doing that in all of our systems. Right. And, well, I will skip that. We would like some community information, but okay, see. So let's look at timestamping. Timestamping is the first thing you will do when your data comes in. Timestamping is important for merging data. And what we often see is people do this kind of loop in their drivers. They wait for the sensor data, they read it, and then they take the system time, and that's the timestamp. Well, that's a problem because if you look at what's happening in the sensor, first there's some acquisition in the sensor, then a sensor does some internal processing, which can be significant for cameras and stuff. Then there's a transmission from the sensor device to the PC. The kernel reads it, the kernel schedules the user space process, and then it wakes up. So what we want for the timestamp is, in the middle of the acquisition interval, but what we get if we do the above is sometime back there. And that can easily be 30, 40, 50, 100 milliseconds, depending on your system. So, and also I should also say the delay is not necessarily constant. In some drivers, you see that people subtract an offset to account for the transmission and all that. But all of these steps here, well, maybe with the exception of acquisition, can be variable length. So you can't just subtract something. Well, there's multiple approaches to remedy that. One is a sensor with a clock. So either the sensor has a clock or you can attach it to a clock line. Then the sensor data includes a timestamp. If you do that, then you know, okay, which point in time does the timestamp refer to? End of processing, begin of processing, middle, something like that. And how is the clock synchronized? And then there's clock sync, clock misalignment, handling, and drift. So, and this gets worse if you need multiple sensors. So how do you synchronize clocks? Well, if you have a big sensor with a microcontroller in it, you can use, if you're between multiple machines, you use NTP, which can do millisecond accuracy. If you have on a local box, you can precision time with microsecond accuracy. If you have your own hardware, you can use a clock line. Many real-time bus systems include clock sync. But yeah, well, that's, I should had one other item here. But that's all high-end. In many senses, you don't have that. So what you then get is you have some clock misalignment between your sensor and your PC. And you need to handle that. And this offset will also drift. That's something that many people are not aware of or don't see the significance. But the thing is, the real-time clock on these systems is never really accurate. There's a quartz in there which has a frequency, which is not usually the exact frequency. And then this frequency also differs with temperature and sometimes with supply voltage and also on. And this is a systematic error, so it really adds up. So it's not like many people expect, okay, maybe there's an error, but it will be sometimes positive, sometimes negative, so it even averages out, but this is not the case. The drift is a systematic error and it will increase. And we see the example here by Olsen. If you are turning 90 degrees per second, which is actually not that fast, and you have an object in 10 meters distance that gives you 60, like clock misalignment of 10 milliseconds gives you 16 centimeters of location error. And 10 milliseconds on an uncompensated real-time clock can happen in just a few minutes, really. I mean, I'm not kidding. You can improve this with better clock chips and all of that, but you will have drift. So the approach is you need to estimate that. Olsen's method is fairly easy. Well, basically, this is another visualization of the problem. You have some scan here, then it's transmitted to the host. There's predictor systematic latency, and then you have jitter, and you want to estimate that. And fairly easy method is actually to use, if you have jitter, use the smallest offset that you ever observed, and that's then your offset. And then for drift, you usually need to do some calibration initially, run your system up to operating temperature, and then you measure the offsets over a long time and you see how it drifts. And then once you have those two items, you can use them to compute a clock drift model and use this model to correct the timestamp that you're getting from the sensor. This is all explained very well by Olsen. An alternative approach is that you have a trigger. A trigger means that the host sends a signal to the sensor device when the acquisition should start. Many cameras, for example, can do this via software. For other devices, you may need to use a hardware trigger line. And again, if you have a software trigger, you need to know the communication delay. In the times of FireWire cameras, we knew that fairly exactly. In the times of gigabit Ethernet cameras, well, that's a bit harder to guess, but you can measure it again. And what you should also know is particularly for high rate sensors, if you don't use a real-time receiver thread, there's a big chance of lost messages, and you need to account for that also. And well, this is not so easy. For the software trigger, you need a real-time process. That's fairly easy. But for the hardware trigger, you usually need custom hardware. And I've seen a couple of scientific papers which say, this is so difficult, and this is so big effort to integrate. So we're using this hugely complicated method to estimate the clock drift. Seriously. It's not so difficult to design hardware, and you can often add this, have an Arduino board, add it to your existing sensor board and do a trigger on that. It's really not that difficult, and it vastly simplifies the whole synchronization issue. So that's why I say this is my preferred solution. Have an explicit trigger, and then you know that when your sensor timestamp is and that it's synchronized. Right. Okay. So that's for one sensor. If you have multiple sensors, you need to store, and if you want to process them together, you need to synchronize. So the simple approach is, you receive data, you store it, and then when some condition holds, you start processing it. And typical conditions for that is when you have new data from all of your sensors, or when the data is the right sequence number or has the right timestamps. Or maybe sometimes you have a most important sensor, and whenever you get new data on that sensor, then you will process. The other approach is you make an explicit request to the sensor and then compute. Of course, that blocks, but maybe not so long. Can be useful. And what we often see in ROS is that people merge on the timestamp. And that's why I explained all the things on how to get the right timestamp. That's a reason for that, because this is fairly easy. This is also working well, but of course the timestamp needs to be correct. And you should know that the message filter synchronizer node makes this quite easy. And there's also, if you have multiple sensors. And there's also a very common case of where you want to merge the sensor with a pose. For example, in a move base, to know where the robot was when the sensor message was taken, there's a TF message filter for that. And the TF message filter is a tricky beast. Right, so the purpose of that is what I just said. You only start processing the sensor data once you know where the robot is. So you have to give it the target frame that you want to interpret the sensor data in, and then it takes that. The first version of that, the one with TF version 1, which is still available and still works, it does a 50 Hertz timer. So what it does is, it registers a new timer, and then every 20 milliseconds, it checks whether the target frame and sensor frame to target frame transformation is available. So this will incur a delay. Just saying it. 20 milliseconds is not too bad, but there is a delay. That's why in the version 2 of the message filter, it uses a different approach. It registers a callback with TF. TF version 2 supports that. And so whenever some new sensor data comes in, then it is being checked whether the transform is now available. Not when new sensor data comes in, when new TF transform data comes in. Then it checks whether it now has a sensor transform and so on. Unfortunately, it somehow does register this callback on every new item of sensor data. And, because this is all cross-thread synchronized, there's a lot of mutexes going on, and this is hugely expensive. So if you have high-rate data, that's not a good solution. We could fix this. Actually, it's not that difficult to fix. But I'm wondering why that is. So if somebody knows the reason for the current implementation, which seems odd, I would like to know. And if nobody comes up to me and says this is done because we need it for whatever, then we're going to change it, because this is really not necessary. Maybe we change it for ROS 2, right? Okay, and so now there's ideal we're working on. Good, and this is a link to this documentation. Okay, so enough with sensors. I want to explain the original example a little bit more to sampling effects in the move base. So, what's sampling? Sampling traditionally means a discrete measurement of a continuous signal. And we often do that in regular intervals. And we also sometimes call the result of that a sample. And this is so, as you can guess from that, this is a term that originates from analog systems which were getting digital. We also use this now in our message-based systems. And in the message-based systems, what we often have is that the acquisition and the use of the data are separated. And so if you do that, this is usually done for modularization, and because one person writes the driver and another one writes an algorithm, and there's many algorithms and just one driver. And so we can do this in two ways. Either the driver can pass this on directly to the user, or the driver puts something into storage, and then the user looks at the storage independently. And in the second case, it's fairly obvious, if you consider it, that if you put something into storage and then somebody else reads it, there's a potential to read it before new data has been added to the storage, if it's in regular intervals. And if that happens, and that's actually okay, if you always read it before new data is being added, then that's fine. But if sometimes you read it just before new data is being added and sometimes you read it later, that's what we call a sampling effect. And here we have that if you have mismatched rates, then you can get this quite often. And rates are affected by scheduling. So even if you have 10 hertz here and 10 hertz there, maybe if the other 10 hertz is always delayed or there's a jitter, you can get these things. And so this is a visualization of that in a very simple example. So what we see here is on the one side we have 3 different tasks, and they always process. And here what you see here is the orange part is where the actual computation is going on, and the yellow part is where it would have been available to run, but something else was running, so it wasn't scheduled yet. And then what we see here is task 1 puts something to task 2, and task 2 is triggered here by that, and then computes, and then task 3 gets it. And then we see, another one for task 1, task 2, task 3, and then another one for from task 1 to task 2. But then before task 3 gets a chance to run, task 1 gives another thing here to task 2. And then task reruns. And so actually this intermediate result from task 2 is lost. And this is also another one where these kind of scheduling glitches can, even if you look, everything seems fine, you can have these effects where some item of data is lost. And if you look at the move base, so the principal processing stages in the move base are first receive some sensor data, in this case I said laser scan, then you want to know where the robot was, receive the pose, merge that, then you use this to mark occupied and free space, perform local obstacle avoidance, and then output a velocity command. And this should be in that order. But if you look at how the move base is implemented, then you see that there's actually 4 different threads in the move base. One is for reading the sensor data. One is for the local cost map. One is a TF thread, which is important for synchronizing. And then we have there's one thread updates the cost map, and then another thread does the local planning. And as I tried, so like these ranges here, they visualize when the process could run in principle. So in any of these times, it could run in principle. And so what this means, for example, the move base plan thread has to be done before the velocity command is output. And it also has to run after receiving the pose, because it gets the pose from odometry. But in between those, it could. It could, for example, run between, after receiving the pose, but before the sensor data and the pose have been merged. And so then it will run before the cost map update. And so this is the same image as before in terms of content. But what we have done here is we looked at these various processing stages in the move base and how much time do they take. And so to narrow down a little bit more of where this strange difference in response times is coming from. And so the red line on the bottom that you see here, that's the delay between when the laser data is coming in and when the pose is coming in. So you see that's almost always very constant. But after that, things start to become very different. So sometimes, for example, as you see here in the beginning, sometimes it takes a while after the sensor data is available until the cost map is actually updated. And that is because the spin thread puts it into a buffer, and then the cost map update thread has a 10 Hertz rate and takes it from the buffer. So depending on what the relationship between when the spin thread puts it in and when the update thread takes it out is, we can get this delay. And then again, the plan thread is a different thread, so again we see a delay between the update and the plan thread, and then the gray part there is just, the planner takes some time to compute. And as we can see, this time to compute for the planner, that's fairly consistent. So, I mean, this could have been an alternative explanation, right? That the planning time is so different, but as we can see, that's not the case. Planning time is actually quite consistent. So, and we did this, as I said, for 5 runs, and each of the 5 runs, we had 3 different targets for the move base to drive to. So that's the data we use here. And so we see not just delays, but also this change in execution order. And then first of all, I should have said before that the sensor rate and the controller rate wasn't synchronized. So now we did that, let's run the controller at the sensor rate. And this gets that quite a bit lower, but it's very inconsistent, jittery. And yeah, again, we have this reordering. And then this is again the one from before, so we refactored that. And that's the result after refactoring. And what you can see here is that suddenly we are getting way below 50 milliseconds. And we are down here. And even the planning time is reduced. That's odd, but that's because there's nothing else hindering it. And if you look at this more statistically, what you could see, this is a distribution of the reaction time for the various parts. And as we could see, this cost map update here that had a really large variance before, and now it's almost 0. And the thing is, and if you put that in numbers, before we had the mean response time from 85 milliseconds, and now we have 9. And it's no longer 60 milliseconds standard deviation, but 5. So, and the max delay is bounded. So this is what you can get if you look at these things with an eye towards the sampling effects and preventing them. And now I will give some ideas on and common practices on how to do that. And I have 2 minutes left. Okay, right, SPC. Right, so architectural choices. Again, just that's good. We call this when the computation is directly caused within the callback, then we call that data trigger. When the actual computation is triggered by a timer, we call it time trigger. For time triggering, what we see in ROS is 2 different patterns. One is you have, ROS timer, and the other is that you have a timer loop where you call spin once. And because we always like to visualize our systems, what we found very useful is to put these things, make these things explicit. So ordinarily, a ROS node is a black box and you don't know what's going on inside. So we have this small visual notation where you say, okay, if we put a T here, that means it's a data triggered system. We can also say there's a timer inside. And if we have an R here, that means it's a register, so something is just stored for later processing. And if we have this sort of data triggered system, we also put the queue size. And then the easiest way to achieve full determinism is have data triggered pipelines throughout. Data in, processing, data out, and do that in a pipeline, and that's perfectly deterministic. In the sense that you don't have reorderings. Okay, so this minimizes delay. If all you care about is delay, that's what you should do. But it maximizes jitter because all of the input jitter, all of the processing time jitter will be directly passed on. And another thing you have to keep in mind is the queue size part. If you put queue size 0, you get everything, but you can get out of memory if you don't keep up. Queue size 1 seems to be a bit frowned upon by people. You can lose data. But actually, it's quite useful because if you only care about the newest data, like if you want to run the laser scan not for mapping, in mapping you usually need all the laser scans, but if you want to use it for obstacle avoidance, you really only need the latest laser scan. And as long as your robot isn't driving really fast. So that's quite useful. And the other things are not as useful as you would think. Okay, the other thing is if you have timers. So timers should be used whenever it's more important that computation occurs in regular intervals. And the absolute maximum reaction time is not so important. Then you should know the timer is not something which is has a global clock or anything, but if you have a 50 Hertz timer, it starts when you create it or when you call start. And what we then see is also hardware devices often start when you start running them. When you open the driver, that's when they start running. So what we have found quite useful is that you have a stage where all the nodes start up, and then after that, you give a trigger signal on a topic, and when the nodes receive the trigger signal, that's when they start the timers. And because that, of course, the trigger signal could also be delayed, we usually do that with, putting a timestamp into the trigger signal, and then it starts on a timestamp. And then, of course, the last approach, which is the one that's mostly used in ROS, is explicit synchronization. And you put a sequence number or a timestamp in the message. Most people do this on the timestamp. But the sequence number, if you have the synchronized starts that I said before, then you can actually do it on the sequence number. And this is also quite useful for many things. Also, when you don't have timestamps, for example, you can still use the sequence number. And there's the ROS2 lifecycle, which we also backported to ROS1, can help you. And this is, just visualizing it. So that means you have to have stamped data here. And if you have across threads, you can use synchronization objects in the same process, which is what we did in the move pace. We just put a condition variable. And of course, the usual concurrency management stuff. And so the last thing, you saw all these timing measurements that I gave you earlier. How did we do that? What we did is we used instrumentation of ROS CPP. We put Linux Trace Toolkit instrumentation in there. And I can say that we're actually just working on making that open source. So it's already the management approval has been done and all that stuff, but I just need to get around to actually pushing it on GitHub. And what we did is whenever there's a message entry and exit, when there's a callback entry and exit, how the queue delay, and in message filters we put trace points. And we have this small trace tools package, which we will also make open source, which is a generic wrapper for the Linux trace toolkit. So yesterday, somebody used ftrace, for example. You could also put ftrace in there, which just worked just as well. And we have a generic model for the trace data and some Python code to analyze that. So if you're interested in that, getting early access, then talk to me. And we have, well, you probably can't read that. Sorry about it. This is just some Python experiment code to run all the stuff and make a plot. OK, so to summarize, and I'm almost in time. So deterministic behavior is not something that just happens. You have to think about it. You have to consider the architecture of a system. And if a non-deterministic system, there will be, 99% of the time your jitter and all that will be OK, but then there will be a switch and then you will be in trouble. I promise it. And all these things, they are not rare. They happen frequently. And then, one of the most important things is make sure you have proper timestamps, use common merging patterns, and design, measure, and repeat. And this is just a call to the community. If there are people interested in this stuff, please talk to me. There's a lot of things we could do. Thank you a lot for attention on this dry topic, I guess, and I'm happy to have questions.
Thank you very much, Ingo. That's definitely informative, and we'll follow up about the TF. Does anyone have questions? We have time for one or two. Awesome.
Thank you for an interesting presentation. I have more down-to-earth question about usage, or not usage of these techniques, but for example, I build robot. How can I, using some empirical checks, how can I determine that my robot is fairly good in this matrix, like of determinism, or is fairly bad? Do you have some kind of questionnaire where you check and you say, OK, so you don't have to apply the majority of this, because in your use case, robot would be deterministic or more or less deterministic, or some kind of scale of determinism. So you don't have to spend that much of effort, because this is something you have to do, like this is not something simple to do. So do you have any, or think of some kind of questionnaire or guide? Thank you.
Yeah, I mean, what we have to look at the architecture of your system, see what your activations are, how you do the timestamping, all that. That's one way. And the other way is just measuring it, and looking. In the trace tools analysis code, there's an analysis which looks at the order in which your callbacks are being called. And if you see that the order is flipping, then you have a problem in that respect. And you can also do this latency measurement. And if you see these switches between low latency and high latency, then you have such a problem. I mean, it's not really like if you don't use package X, you won't have a problem. It's not like that. You have to look at the architecture.
Thank you.
Yeah. And one more question. Ingo, if you could answer on this.
Sure.
Hi, Ingo. Thank you for your interesting talk. Short question related to RT preempt. So you were talking about it to fix some of the wake-up delays, but does it? How does it help? Does it get you rid of the outliers, or does it also decrease the delay itself?
So we're not changing RT preempt. What I was trying to say is that if you don't use RT preempt, then even if you have a real-time scheduled process, you will still see these outliers, because the kernel can still override it.
Yes,
that's what
I
I'm saying.
that,
If you use RT preempt, you won't see those.
You won't see the outliers anymore, or not even. Okay.
At least, I mean, the open source automation development lab did extensive test cases for years, and with RT preempt, and they didn't see any.
Okay.
So I think that's good enough for us.
Thanks.
Okay.
Thanks again, Ingo.